and what it means to me. Oh. I see. Okay. It was longer than expected. I think that's what you're trying to say. Yeah, when I did the exam, I multiplied the time by 4. The time it took me to do it. Obviously, I've written the exam. So I multiplied it by 4 and it came out to about 120 minutes, so 2 hours. Yeah, so it should have taken about 2 hours, which gives you about half an hour to go back if you want to check anything, but enough time to scan it and pretty much submit everything. The prime example was difficult. I don't know, I forgot which one was a prime example, actually. Prime example. Exam 2. Number 4. Oh, yeah, that one. Can you find a formula rule of the M terminal sequence? Hopefully you didn't get a hangover or something. Well, remember that for the first, that's why I wrote for the first 5 questions, just give the answer. You don't have to show your work, just give the answer. The other ones, you had to show your work. But that's pretty much going to be the structure of your next exam and the final as well. Oh, number 11 was a little bit tough. I will give it that one. But again, we'll go over them. And I will post the solutions. I don't think I even posted the ones. I think I already posted the ones for exam 1 online, right? I don't remember. Sure I did. Now, for number 4, I can tell you that one right away, actually. So the rule for number 4, I don't think I posted them yet. I'll deal with that later. Okay. Well, we'll worry. Okay, so first let's worry about this, and then we'll deal with that. Let me do this. Okay, so that's the last thing we talked about. It could have been tougher as well because it was on various subjects and it didn't focus on just one chapter like the last one. The last one only focused on one chapter. So that's why it could have been difficult as well, a little bit more difficult than the last one. The last one, you only had to focus on one chapter. And then on this one, you had to focus on various chapters and sections. Okay, now, so next week you'll have a quiz. I think this is quiz 5. It's going to be on sections, and I'll tell you what sections. Once I open it up. There it is. This is what I want. 6-3, 6-5, 7-1 through 7-2. Which obviously we're going to do 7-1 and 7-2 today. Okay. It's going to be, oh, let me open up the calendar. Sorry. Oops. It's going to be on 10. No, we're on the 11th now. 11, 10. And also is going to be due to 11/12/2021. Before midnight, as always. I'm gonna try and post the exam one solutions. I thought I already posted them, but I'll post them. And then, so I won't forget your third exam. I'm already telling you now. So your third exam, unfortunately, it's gonna fall on the last week of November, which is entirely November, which that's when Thanksgiving's at as well. So you're only gonna have honestly a couple of days to work on that one. You're only gonna have probably like, well, no, I'm gonna give you Monday to Friday still. Yeah. So it's gonna be on 11/22 through no, the final will be the following in 2 weeks after that. So it's gonna be 11/22 through the 24th. So you're only gonna have 3 days, and that's the nature of the beast for this one. It's just gonna be like 3 days. But I'm gonna leave it open for 3 days. I don't want to put it on Thanksgiving, which is the 25th or 26th, because let's be honest, no one's gonna do them. So I'm gonna leave it open for 3 days. So unfortunately for the third exam, it's gonna be 3 days. You're still gonna have 2 hours and 30 minutes. Still gonna be 2 hours and 30 minutes. And it's gonna be the same structure like the last one, where you have a couple quick questions you have to answer, you show the work, and then you show work on the last ones. It's gonna be on sections, well, the ones I haven't tested you on, which is pretty much chapter 5, chapter 6, 7, and 8. Because we will finish up to those chapters by that time. Okay, we will be able to finish those chapters by that time. Obviously, only the sections that we are going over, no other sections. So I'm not going to do, like, for example, we're going to skip section 7.3. So I'm not going to test you on 7.3. It's only going to be section 7.1, 7.2, and 7.4. But that looks like what your third exam is going to be at. Any questions on what I just said? No? Okay. And again, it's going to be the same structure, and hopefully everyone was okay with, hopefully, well, sorry, it's going to be the same structure. Well, I'm going to give you like first couple of questions are going to be just short answer. Just give me the answer. And then the other ones are going to be show your work. So that's why I said make sure you read the instructions. And also on the exam, you read the instructions, just the very first ones. The lowest exam grade is not dropped. It is replaced by the final, assuming you do better on the final. That's how that works. So it's not dropped. Mm-hmm. Yes, by just answering it, it means no work. Exactly. So you don't have to show work. I'm being that's why I was very precise. I just want the answer. Well, the first ones, that's why I just said, just give me the answer. I think I literally said show no work. Just give me the answer. For the other ones, I did say show work. And again, that's how your final is going to be structured. That's how your next exam is going to be structured. So now you have another heads up. Okay. Sweet. I feel like I'm missing something. No, that's pretty much it for right now. Okay. Now again, your third exam, unfortunately, it's going to be given in a time period of 3 days, and it's just because of the holidays that are coming up, and we kind of have to abide by them. So that's why I am letting you know that the next exam you're only going to have 3 days. So make sure, and I'm giving you plenty of time to know ahead of time that you're only going to have 3 days for this exam. Okay, 3 days. Good? Any questions? Okay. Now, before I forget too, because I know I'm going to forget, on 11/11/21, it is Veterans Day. And I believe there's no class on Veterans Day. I'm going to check the catalog real quickly, but I believe there's no class on Veterans Day. So next Thursday, and I think that affects you guys. It does. It's a Thursday. There is no class. Which means I'm not going to have no office hours either. Any questions on that? No? Okay, sweet. So now let's start with chapter 7. So section 7.1. Section 7.1. And if we have time towards the end of class, I'll talk about number 4 of the exam, if you're still curious about that one. Okay. I'll leave this up there because maybe someone didn't copy it yet. Okay. Now, we're gonna start talking about, well, pretty much chapter 7 is all gonna be about probability. So we're gonna start talking about probabilities. Now, just in case you don't know, this is what a die is. A die, for us, is a 6-sided cube, okay? That's gonna have numbers, such as these. So this is a die. And the numbers that it has are 1, 2, 3, 4, 5, and 6. Okay, that's what a die is. Any questions on that? I'm just trying to make sure everyone understands what's a die. Now, when I say dice, that is plural. So that means more, that means 2. Okay, so dice is plural, and that means 2. So make sure you know the difference between a die and dice. Dice is plural, so that means two dice, and die is singular, so it's only one. And again, the die has the numbers 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Pair of what I'm trying to do on, and I'm gonna put something on the chat because we're probably gonna use this later just in case. So let me get it so you can get it so you can download it on the chat. Actually, I'll just have it ready. And then I'll tell you when to check the chat. Okay. Sweet. Okay. Now, that's what a die is. Okay, it's a 6-sided cube. Numbers 1 through 6. Nothing more, nothing less. So let's look at this example. What is the probability that a fair die comes up with a number that is less than 5? Okay, so if you know the answer to the question, that's good, but don't answer it right now, okay? Don't fully answer it right now. What is the probability that a fair die comes up with a number that is less than 5? Okay, so first questions are, or first concerns, if you don't know anything about this, which is fine. What is a fair die? Well, a fair die means that it's a 6-sided cube that's fair. In other words, it's not going to try and land on any number specifically. All numbers have an equal chance or equal likelihood of coming out. So if you roll a die and you roll it and you roll a die, then the number 2 has an equal chance of coming out as the number 5. The number 4 has an equal chance as the number 6 coming out. And the number 6 has an equal chance as the number 2 coming out, and so on and so on and so on. That's what it means by fair die. Now, if it said a loaded die, that means it's loaded in terms that it is going to land on a specific number more often than on another one. So in other words, you can cheat with that die. Okay? Any questions on that? Any questions? Okay. So that's what it means by a fair die. Now, what is the probability that a fair die comes up with a number that is less than 5? Okay. First of all, we need to understand this entire thing. We need to, what does it mean for a number to be less than 5 in a die? Well, in a die, if you roll it out, you want a number that's less than 5. In a 6-sided die, you have 1 through 6. So what numbers are you looking at? 1, 2, 3, 4. Do you look at 5? Yes or no? Right. No, you don't look at 5. So this is known as your event. This is your event. Okay? That's your event. So the event here is a number that is less than 5. Usually we let a capital letter represent the event. So let's say capital letter E. And this represents a number that is less than 5. Actually, let me write it like this now. Event E. Okay, that's what an event is in this scenario, our event is a number that is less than 5. But what really is an event is pretty much a subset. An event is a subset of the sample space. That's what an event is. An event is a subset of the sample space. And you're going to hear the word event a lot. That's why you need to understand what it is. A subset of the sample space. Now, the sample space S. That's too tight, so let me give myself some space. So E is a subset of S. Okay, now, what's a sample space if you don't know what a sample space is? Well, here's a sample space. A sample space, the set of possible outcomes. That's what a sample space is. It is the set of possible outcomes. So in this scenario, our S, which is the sample space of a fair die. Well, the sample space of a fair die is pretty much all the outcomes when you roll a die that can possibly come out. That's 1, 2, 3, 4, 5, and 6. That is the sample space. So the event is a subset of that sample space, and that makes sense. If you look at the events, a number that is less than 5 is the set of these numbers, which clearly is a subset of these numbers here. Okay? Any questions so far? Obviously, we haven't even answered the question at all, but any questions so far? Okay. Now, the next thing is, what is probability? That's too dark. What is probability? Well, how do we define probability? Okay, well, this is how we define probability. Definition. If S, which means a sample space, and again, it's a capital S, so don't get it confused. If S is a finite, non-empty sample space of equally outcomes. Now, what do I mean by equally outcomes? In other words, each number in here, for this example, has an equal likelihood of coming out when you roll a die, or it has an equal probability of equally outcomes. And E, the event, is an event that is a subset of S. Then the probability of E is lowercase p, it's a lowercase p of E, so the probability of the event is equal to the absolute value of E over the absolute value of S. And that's pretty much it. So in other words, It is the number, well, actually, that's not the absolute value, that's the cardinality. It is the cardinality of the event, the set of the event, divided by the cardinality of the set S. Any questions on that? Any questions on that? And again, some of this may look familiar to some of you, not all of you, but maybe to some of you, it looks very, very, very familiar. But that is what a probability is. It is the cardinality of the event divided by the cardinality of the sample space. Okay. Any questions on that? Okay. So for this example, what is the probability of that a fair die comes up with a number that is less than 5? Well, our probability is, and this is how I'm going to write it, the probability of E, capital E, is a cardinality of E or divided by cardinality of S. Well, the cardinality of E is 1, 2, 3, 4 divided by the cardinality of S, which is 1, 2, 3, 4, 5, 6. So my probability is equal to 2/3. 2/3. Any questions on that? Which if you have your calculator, I will leave it as a fraction, honestly. I will prefer it as a fraction. I don't want it as a percentage unless I state it. I don't want a decimal unless it's stated or given to you in that form. But other than that, leave it as a fraction. Okay, which is approximately 0.6. And this goes on forever. So in terms of percentage, that's about 67%. So approximately 67% if you're looking at it like that. So that means if you roll a die, there's a 67% chance or probability that it's going to come out with a number that's less than 5. That's all this is saying. Any questions? Yes, no? Just trying to make sure. Okay. What is the probability? So let me copy the exact same question. What is the probability of the fair die that comes up let's say five or greater, that comes up greater than or equal to 5? What is the probability that a fair die comes up with a comes up greater than or equal to 5? Okay. Well, with a number, I should say with a number, comes up with a number to keep it the same, with a number greater than or equal to 5. Well, let's determine our solution. What is my event? First, you always want to identify your event. I know it seems like a tedious question. I know it seems like a tedious thing, but you always want to know what the event is. So in this scenario, what is the event? What is the event? Right, but what is the event? Not what is the event telling you to do? Roll a 5 or 6, right? So the event is telling you to roll a 5 or 6, or in other words, the die comes up with a number greater than or equal to 5. Or, yes, you could have said, and I would accept it as well. You roll a 5. Or 6. Yeah, that's fine. I would have accepted that because that does make sense. You roll a 5 or 6. So if you want to write the set, you could. It is 5 comma 6. That's pretty much it. Okay. So what's the probability of E? Well, remember the probability E is the cardinality of E divided by the cardinality of S. Could we just write the set, or do we have to write out the event is? No, you could write out the set and I'll be fine with it. But if I say, that's actually a good question. Do I want you to write as a set, or do I want you to write it in words? You could do either one. I'll accept either one. I'll accept either one. Okay. Now, the probability of the cardinality of E, that would be 2 divided by the cardinality of S. What is S? Well, that is the sample space of the third die. If you don't know the sample space, it's always best to write it out. 1, 2, 3, 4, 5, 6. So that's going to be 2/6, which is simply 1/3, which is approximately 33%, or 0.3. Which, if you want to change it to percent, that's approximately 33%. Any questions on that? Okay. Let's say the same question, but now I say this. What is the probability that third die comes up with a number greater than 6? Well, in this case, what is my event? What is my event? What is the probability that third die comes up with a number greater than 6? What is my event? It ain't empty. What is my event? It ain't 0. What is my event? So I'm not asking for the answer. I'm asking for what the event is. Right. And the event is rolling a number that's greater than 6. So rolling a number that is greater than 6. You can't say roll 6 or 7 because it has to be a number greater than 6. So the event can't be rolling a 6 because that already contradicts that. It can be or 7 because what number is greater than 6? Well, 7 is greater than 6, but what about 8? What about 9? What about 10? What about 9? What about 11? What about 500? You see what I'm saying? You will actually have to write all those numbers down. So in this scenario, instead of writing it as a set, you just literally write out in words what the event is. Rolling a number that is greater than 6. That's all you're doing. Rolling a number that is greater than 6. Okay. Well, here we go. So that means I need to roll a number that's greater than 6. But my sample space is 1, 2, 3, 4, 5, and 6. No number there is greater than 6. So the probability of the event is a cardinality of E and the cardinality of set S? Well, that's just simply 0 over 6, which is 0. So it is not possible. It is not possible to roll a number that's greater than 6. Now, by doing this also, hopefully you realize something. Note, the probability of an event has to be greater than or equal to 0. So the probability of an event can never be less than 0. It can't be less than 0. Okay, so you can't have a negative probability. That doesn't make sense. It's the equivalent to saying it's not possible. Well, if the probability is 0, then it is not possible. Does that make sense so far? Any questions on that? Okay, another thing about the probability. If you do look at the first two examples that we did, which is this one, what is the probability that a fair die comes up with a number that is less than 5? Well, the probability of that was 67%, or 0.6, or 2/3. I know we're looking at that. Then this one said, what is the probability that a fair die comes up with a number greater than or equal to 5? So the other numbers, 5 or 6. And it is 1/3, 0.3, or 33%. So notice that if I decide to add these two numbers, if I decide to add 2/3 plus 1/3, I will get 3 over 3, which is equal to 1. So what I'm trying to get at is this, that the maximum that a probability can be is always 1. So the probability of an event must be between 0 and 1. Probability of events must be between 0 and 1. Any questions on that? Any questions? Okay. Now, let's do a couple more examples. So if your probability is greater than 1, then something's wrong. So make sure note that. Example. Oops. What is the probability that a randomly selected day of a leap year with 300 is in April? What is the part that randomly selected day of a leap year is in April? Okay, so let's try and figure this one out. What is the probability that randomly selected day of a leap year is in April? Well, how many days are there in a leap year? So first you want to figure out your sample space. So we need a sample space, right? So my sample space is the number of days in a leap year. So number of days in a leap year. Well, how many days are there in a leap year? Well, if you don't know about a leap year, okay, how many days are there in a year? 365 days are within a year. Exactly. So more than 10 for sure. That is true. So the number of days in a year is 365. A leap year means that there's one every 4 years, I believe, there's one extra day for sure. So that means we are talking about 366 days. Okay. Now, what is my event? What is my event here? You want to identify your event as well. What is the event? What do you mean by April? Close. So the event is selecting a day in April. That's the event. Selecting a day in April. Okay. Now, someone already kind of said it. How many days are there in April? There are 30 days in April. Okay. So my probability of the event is the cardinality of E over the cardinality of S. So in other words, the number of days in E. Well, the number of days in E is 30 days divided by the total possible outcomes. Well, in a year, there are 366 possible outcomes. So I'm going to take 30 and I'm going to divide it by 366. And that's the answer. That's it. You don't have to do anything else. You can divide it with using your calculator if you want, which is going to be approximately 0.08 if we're rounding it, obviously. So no way looking at it, if you want it in terms of percentage, there's an 8% chance of selecting a day in April that falls within a leap year. Any questions? Seems like a really small number, but it's only a couple of days overall. Any questions on that? No? Let's try a couple more. Or am I going too fast? You guys are good? Okay. Let's try another example. What is the probability that a card selected at random from a standard deck of 52 cards is an 8. Okay, so again, first things you want to do is determine your sample size and your event. What is the probability of hitting a Yahtzee? Honestly, I don't know because I don't even know what Yahtzee is, nor have I ever played it. So that's why I'm trying to keep things where people have played or possibly. Oh, 6 die of the same row. 6. Oh, 6 dice. Maybe we'll try that one out. We'll see. 6. We'll try it on this maybe. We'll see. That's kind of like interesting. I don't know. We'll see if we'll get it right. Okay, first let's do this. What is the probability that a card selected at random, from a standard deck of 52 cards is an 8? Well, first, you want to understand your events. You always want to write your event out because then it's gonna tell you what it is. Obviously, if I give you this question on like just a short answer, you don't need to write down the event. You just literally got to give me the answer. So the event, what is the probability that, so what is the event here? What are we trying to do? What do you mean by 8? Oh, okay. So the event is selecting the 8, selecting an 8. Selecting an 8, exactly. So that's the event, selecting an 8. Sweet. Now, what is my sample space? Well, my sample space is 52 cards. Obviously, I'm not going to write down all the cards, but my sample space is 52 cards, right? That's my sample space. Now, if I written it all down, it'll be the set of 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, but those are the hearts. Then I have to write the other ones down, then the other ones, and the other ones. So in the end, it's just 52 cards. So the event of selecting an 8. So here we go. The probability of the event E is equal to, well, how many 8s are there in a 52 card, in the standard deck of 52 cards? How many 8s are there? Exactly, there are 4 8s. There's 1 8 for each suit. And since there's 4 suits, then that means there are 4 8s. And then divided by the total possible outcomes. Well, the total possible outcomes is 52. So 4 divided by 52, and that's it. Which you can reduce this if you want to 2 divided by 26. Well, actually, I could divide more than that. 1 divided by 13. So 1/13, which is approximately 0.08 or 8%, if you cared about the percentage. Any questions? Okay. I'm curious about this one. Let's see if we can do it. Yahtzee. So it's 6 dice of the same row. So give me an example of winning. What will be an example of winning? Or saying Yahtzee, whatever you have to do. So you don't know. Okay, then never mind. Let's deal with it later then. Okay. Now, let's try another example. Something a little bit different. What is the probability that a 5-card poker hand and we're going to do a couple examples of this. A contains exactly 1 ace. Okay, so we're playing five card poker. Now, 5 card poker is used with a standard 52 card deck. So standard 52 cards. That's it. Okay, no jokers. We're not allowing jokers. That will be 54. So we're just doing standard 52 card deck. So the jokers are removed. Now, an ace can be considered high or low. It could be counted as high or it can be counted low, depending on the hand. Now, obviously, if I give you a problem that deals with the ace and determining that deals with the ace and trying to figure out if that's high or low, I will tell you ahead of time if it's high or if it's low. Okay. If it's high, it comes after the king. If it's low, it comes before the 8, before the 2, I should say, before the 2. So what is the probability that a face card, no, sorry, what is the probability that a 5-card poker hand contains exactly 1 ace? So if you have 5 cards, what's the probability of having exactly 1 ace? Well, how do we do that? First of all, let's deal with the fact that we want. Well, let's understand our events. Our event is selecting an ace. That's the event. Okay, my sample space is 52 cards, so that is not changing. Okay, so the probability of E is equal to the probability of selecting an ace divided by the sample. Well, actually, no, the sample space is not 52 cards. Actually, the sample space is this. You have 52 cards, but you want a 5-card poker hand. Does order really matter? No, order doesn't matter. So my sample space is actually 52, choose 5 cards. So that's already going to be on the denominator. That's for a fact. 55, choose 52, choose 5. Okay, now let's look at our numerator. So I already understand what the event is. The event is I want to select 1 ace, exactly 1 ace. Well, let's select that ace first. How many ways? Well, first of all, how many aces do you have in a deck of cards? And 4, right? So, does it matter which ace you get? No, it doesn't really matter. You just want an ace. So, there are 4 ways on how to select an ace. So, one way you can write it out is 4, choose 1. What this is saying is out of 4 aces, pick 1. Because that's what you're looking for. Out of 4 aces, pick 1. Times. But that means, how many cards in my hand do I have right now? 1. I only have 1 card in my hand. I need 5 because it says 5-card poker. Well, that means I need to select how many more cards? 4. Now, it doesn't matter what the cards are at this point. No, it doesn't matter. You're right. The cards don't matter. But we want to guarantee for sure that we're not going to pick an ace. I want to guarantee for sure that I'm not going to pick an ace because I want exactly 1 ace. So that means I got to pick 4 more. But because I want to guarantee that I'm not going to pick another ace, I'm going to take out all the aces out from that deck, from that 52 card deck. So that means I have now 48 cards, and I'm going to choose 4 of them. So my solution is just pretty much this. Well, no way you could write this is 4 times 48, choose 4 over 52, choose 5. because 4 choose 1 is the same thing as saying 4. Now, if you do this on your calculator, and I'm trying to do it, I'm going to do it really quickly. It is approximately 0.3. So about 30%. It's actually not that bad when you think about this. Any questions? Any questions? We'll do another one, obviously. We're going to do another one. But any questions? Now, same instructions. What is the probability that a 5-card poker hand? So we're still talking about 5-card poker hand, but now I'm going to do part B. Now, part B, I'm going to write down here. Contains at least one jack. Contains at least one jack. Okay. So again, you understand your event. What is my event here? Has a jack, right? Selecting at least one jack, right? Selecting at least one jack. And do not use something like this because this doesn't make any sense. I know what you're trying to say, but this doesn't mean at least one jack. Okay? So be very careful with your notation. Now, what does it mean to have at least one jack? Well, that means that you could have one jack, 2 jacks, 3 jacks, or a maximum of 4 jacks. That's what that means. So how do we do this? Well, again, my sample space is still 50 choose 5. So let's say I want to find the probability of this event. Well, here we go. I know my sample space is going to be 52 choose 5, so I'm just going to write that down because I have to have 5 cards in my hand. So let's first do the probability of selecting one jack, because you want at least one. Well, how many jacks do we have? 4. So I still want to, so let's select our jack first. So I'm going to say 4 choose 1, selecting our jack. But that means I have 4 cards left because I want 5 cards in total. But this hand should only contain 1 jack, which means my other 4 cards, there better not be a jack in there. So I'm going to remove them. So that means I have 48 choose 5. Does that make sense so far? Okay, but am I done? No. Why? Because the rule says at least 1 jack. So that means I need, what happens if I have 2 jacks? Well, to select the probability of selecting 2 jacks is the denominator is still 52 choose 5. Oh, I'm sorry, it should be choose 4. Thank you very much. I messed up. Thank you. Okay. Now, for 2 jacks, I need to have 2 jacks. Well, again, I have 4 jacks. I'm going to choose 2. So I'm picking my jacks first. I'm getting that out of the way. Now I have 4 cards. Well, no, I have 3 cards left. Obviously, I don't want no jacks because the whole point of this one is 2 jacks only. So 48, choose 3 now. But I still have the chance of at least one jack. So there's a possibility of 3 jacks. Well, what's the probability of that? Well, again, let's pick our jacks. There's 4 jacks, but we want 3. So 3 times, well, now I have 3 cards in my hand, and I want to pick 2 more. So 48, choose 2. Right? And then we have 52 divided, choose 5, because we want a probability. Sweet. But now we still have the possibility of having 4 jacks. Well, again, we can do 4, choose 4. So we're actually taking all the jacks. Technically, that's just saying 1. There's one way how to do that. Times 48, choose 2. Right? Divided by 52, choose 5. In the end, we're going to add all of this. And that will give us a probability of approximately 0.34115,80017. And there's a reason why I wrote all of this one out, like the entire decimal. Should it be 1 or which one? Oh, 42, choose 1. You're right. Okay, thank you. 48, choose 1. Thank you. Because we only have 1 card left. You're correct about that. Any questions? And that's what Heidi won in her sleep. Then that's a little bit different. Obviously, the probability would change there. Okay. So for right now, let's take a 5-minute break and then we'll do another one. Okay. So let's take a 5-minute break and then we'll continue. Okay, and we're back. Okay, now there is another way how to do this actually. There is actually another way how to find contains at least one jack. What's the other way? Another way of looking at it is this. You already know that for a probability, it has to be between 0 and 1. So the max that any probability could be is 1. The max what this probability could be is 1. Okay. So another way you can view this problem is the opposite of E, or in other words, the complement of E. Now, the complement of E is denoted by E bar. So that means the complement of E. So we could look at the complement instead. So what would be the complement of at least one jack? So in other words, what is the negation of that? What is the negation of at least one jack? No jacks, exactly. Selecting no jacks. Okay, so what's the probability of selecting no jacks? Well, let's determine that. The probability of selecting no jacks is, well, since you don't want no jacks, you want to guarantee that there are no jacks in that deck of cards. So you're going to remove all the jacks. That means you only have 48 cards. And you're going to choose 5 of them. So 48 choose 5. Divided by the total possible outcomes, which are still 52 choose 5. So that's a probability of selecting no jacks. Okay. So if I want the original, which is a probability of selecting at least one jack, then all I have to do is keep in mind that the probability of this event, selecting at least one jack, plus the probability of complements should equal to 1. It should equal to 1 because these are total complete events, the complete opposite events. So that means that another way of looking at it is that the probability of E is the same thing as saying 1 minus the probability of E complement. So that's going to be 1 minus 48 choose 5 divided by 52 choose 5, which in the end does come out to approximately the same thing, 0.3411580017. So there are 2 ways on how you could do this problem. By using the complement. And that's actually a theorem, theorem 7.11. Let E be an event in a sample space S. The probability of the event E bar is equal to S minus E, the sample space minus the event. The complementary event of E is given by P of E bar is equal to 1 minus P of E. So it's pretty much the same thing we did. The only difference is instead of subtracting the P of E, we subtracted a P of E complement to help us find P of E. What's your question?
Oh, never mind. You just clarified it. P PUE plus PUE complement, right?
Yes.
With pink part. Thank you.
So P of E plus P of E bar. So I'll put the bar there. So you can see that better. So again, the complement can, using this term can actually help us find questions like this, solutions to this type. So instead of doing it the long way, which is still correct, if you actually got your calculator and actually did it, you sum it up, you find each one, add them all up, you're gonna get the same thing as this. But some people might view it simpler looking at this than the other way. It really depends on the person. Both are correct. I will mark both correct because they are correct. It just depends on how you write it out. Any questions on that? Okay. Now, let's try another example of this. What is the probability? And I think this is where you're gonna have to look at the chat. I'll put it again because I think it got. Trying to put it in the chat. There it is. You're gonna need that one. What is the probability that when two dice, so now we're talking about plural, are rolled, the sum of the numbers on the two dice is greater than 2. So everyone's gonna have to look at the chat for that one. Now, here's the reason why you're gonna have to look at the chat in a second. Solution. First of all, what is the event? What is the event here? Sum of two dice is greater than 2. Exactly. We can sum it up in how you get to sum it up. Yeah, you can just sum it up as that. Sum of two dice is greater than 2. Now, what is the sample space of that? What is our sample space? Well, our sample space, you're rolling 2 die. So one way you can look at it is an order pair. You roll let's say you roll the first one, it's a 1. Then the second one could be a 1. Then the 1, and then the second one could be a 2. 1, and then the second one can be a 3. 1, the second one can be a 4. 1, the second one can be a 5. 1, the second one could be a 6. And you could do this the same thing with 2. 2 goes, you roll a 2, but now the second one's a 1. You roll a 2, the second one's a 2. You roll a 2, the second one's a 3. You roll a 2, the second one's a 4. You roll a 2, the second one's a 5. Roll a 2, the second one's a 6, and so on and so on. In the end, you will get something that I put on your chat. You will have 36 outcomes. There are 36 outcomes. And you can see why there are 36 outcomes. Because there's going to be 36 different types of ordered pairs. So if you look at the chat and what I put on there, the little screenshot, you see all the possible outcomes of rolling 2 dice. So in terms of the Yahtzee one, the one that you're thinking about, if it's 6 dice, 6 times 6 times 6 times 6 times 6 times 6. So 6 to the 6 possible outcomes you're looking at. Okay. So how do we do this? Well, first of all, one way to do it is to literally count all the ones that add up to 2 or greater than 2, because that's what it says. sum of the numbers that are greater than 2. So we can add up all of those. So that's one way how to do it, and you're going to come up with an answer, and I'm sure your answer is correct, assuming you're counting correctly. But another way of doing it is if I do the sum of two dice is greater than 2, and I add its complements, meaning that I'm looking at the complements of that event, it should equal to 1, right? Because by that theorem, the probability of E plus the probability of E complement should equal to 1. Right? So the question is, what is E complement then? What is the event of E complement? Sum is less than 2, close. You're missing something. Right, less than or equal to. So if we find the sum is less than or equal to 2, and subtract it from 1, meaning I do P of E is equal to P of E bar, sorry, 1 minus P of E bar, that's going to help me find P of E, right? Because I already know this is true by this theorem. So if I find this instead, the probability of the complement, and subtract it from 1, it'll help me find P of E. And actually, this one might be a little bit quicker. As it turns out, it is a little quicker because we're just interested in the sum that's less than or equal to 2. If you look at all those possibilities, all the ones you've written down, there's only one possibility right there, right? It is 1, 1. Anything beyond that is going to be greater than 2. So I can say, okay, the probability of E is equal to 1 minus the probability of E complement, well, that's 1 out of 36 outcomes, which in the end, this is 35 over 36. And whatever that is, I think it's like 98% or something like that. Let me check. 97%. So this is approximately 97%. So the probability of rolling a pair of dice whose sum is greater than 2 is 97%. Which means, what is the probability then of rolling snake eyes in terms of percentage? Of rolling snake eyes, meaning 1 and 1. Slim to none. 1 out of 36. So it's actually a 3% chance, a 3% probability, right? Because 1 minus 97%, that's 3%. Or 100% minus 97% is 3%. Or 1 out of 36 is 0.03 approximately. And that's the probability of rolling snake eyes. Sweet. Now, let's try one more example and then we'll go to the next section. So again, to answer I'm not going to fully answer your Yahtzee problem, but not right now because we're moving on from the section. But the idea is if you have 6 dice, so 6 dice. So you have 6 dice. You have 6 times 6 times 6 times 6 times 6 times 6. 6. So you have 6 to the 6 outcomes. Which I really don't know what that is. So you're looking at 46,656 outcomes just alone. Because of you can roll a 1, 1, 1, 1, 1, 2, 2, 2, 1, 2, 2, well, 1, 1, 1, 1, 1, 1, 1, 1, 1, comma 2, 1, 1, 1, 1, comma 3, and so on and so on. That's a lot of outcomes. Okay. What is the probability that a positive integer not exceeding 100 selected at random is divisible by 2 or 9. What is the probability that a positive integer not exceeding 100 selected at random is divisible by 2 or 9? So again, you want to understand what the event is. What is the event? What is the event? A positive integer less than or equal to 100 is divisible by 2 or 9. Right. Or to put it simply, a number divisible by 2 or 9. So a number, I should probably be more specific than that. Less than, no, you're right. I should probably write the positive. So a positive, so I'll just do this. A positive integer, I was trying to make it positive integer less than 100 is divisible by 2 or 9. Now, here's the interesting about this one. So a positive integer less than 100 is divisible by 2 or 9. Technically, and actually it is true, there's two events here. E sub 1 and E sub 2. There's two events. Why are there two events? Because it could be this one first. E sub 1 could stand for a positive number or positive integer less than 100 divisible by 2. And then you have the other possibility, which is you have a number that's divisible by a positive integer less than 100 is divisible by 9. So there's two events here technically hidden. Because honestly, this is what we're going to be looking at, right? We're going to look at these two events. We're first going to find out how many numbers are divisible by 2, and then we're going to find out how many numbers are divisible by 9. So technically, we have two events here. So let's figure out the probabilities of event E sub 1 first. Now, how do we figure that out? How do we figure that out? Well, first of all, how many numbers not exceeding 100 that are positive integers are divisible by 2? How can we even figure that out? $100 divided by 2, exactly. We have 100 numbers. We can divide that by 2. So I'm going to take 100 numbers and divide it by 2. If I want to figure out how many of those are divisible by 2. And then what are we going to divide it by? Whatever answer we get. What are our total possible outcomes? 100, exactly. What about P of E sub 2? So what if we're interested in finding all the positive integers less than 100, but divisible by 9? What do we do? $100 divided by 9. Right, and then we divide by the possible outcomes, which is 100. The only thing is we have to be a little slightly careful here. Why do I mean by that? You'll see what I mean in a sec. 100 divided by 2 is it breaks down to 50. So this breaks down to 50. So we really have 50 over 100, which that makes sense. But this one doesn't break down nicely. You get 100 divided by 9, which is 11.11111. So we have a problem here. The problem is this shouldn't be a decimal because there's no such thing as 11.1 numbers. Right, we're gonna have to use the floor function. And that's the general thing with these. You want to use the floor function. Now, why the floor function and not the ceiling function? Why not the ceiling function? Why the floor function? That will give one more, exactly. If you use the ceiling function, you round up to 12, and you're saying 12 numbers that are divisible, 12 numbers between 0 and 100, between 1 and 100 are divisible by 9. But that's not true. There's only a couple of numbers. There's only 11 numbers that are divisible by 9, between 1 and 100, exactly. So these are my two events. And because it's OR, what am I most likely going to do with these numbers? What am I mostly going to do with these? Add, exactly. So the probability of E is actually the probability of E sub 1 plus the probability, or is actually the union of these two, I should say, which is the same thing as saying the probability of E sub 1 plus the probability of E sub 2. Okay. Now that's going to be 50 over 100 plus 11 over 100. Now, we're not done yet because there's something careful that we messed up here, and I'm telling you we messed up. We got all the numbers that are divisible by 2, and all the those that are divisible by 9. However, I think we double counted. And what do I mean by double counted? Does anyone understand what I mean by double counted? If you do, explain, what do you think we double counted? Exactly, the numbers that are divisible by both. So what about the probability of the numbers that are divisible by both? So the intersection of those. How do we figure that out? Right, 18. 100 divided by 18, we do a floor function as well and divide that by 100. Why 18? Because if they're divisible by both, that means they're divisible by 2 and 9, which is 18. The multiple of those is 18, and that turns out to be 5. 5 divided by 100. So we make sure we subtract the intersection. And whatever that is, that's our solution, which turns out to be, what is that? 61, 45, no, 46, no, 56, wow. 56 over 100 or 56% if you want to look in terms of percentage. Now, this concept of subtracting the intersection is another theorem. But you've seen that before because we've done it before. But now we're talking about probabilities. Theorem 7.1.2. Let E sub 1 and E sub 2 be events in the sample space S. Then P of E sub 1 union E sub 2 is equal to P, the probability of E sub 1 plus the probability of E sub 2 minus the probability of the intersections. Obviously, the probability of the intersection is 0, then that's even better. But sometimes it may not be, and sometimes it may be. And that ends section 7.1. And this is what we're learning now. Obviously, we have enough time to at least start section 7.2. Will we finish it? Highly doubt it. But this is what we're going to start talking about now, probabilities. And some of you might find this a little bit more fun. Any questions? Okay. So let's do section 7.2 now. Section 7.2. Now, we're going to do an example we already done. So I'm going to rewrite it, but let me copy it. Where'd it go? This one. What's the probability? Randomly selected day of a leap year is in April. Now, we obviously knew how to do this one. We counted how many days. And then we did, okay, 30 divided by, we counted the number of days in April, and we divided by how many days of the year in a leap year, which is 366. Now, another way of looking at this, or another way of doing it, is this way. In April, there are 30 days. Right? 30 days. No, each of these days have an equally likelihood of occurring. So the first day could occur, the second day could occur, the third day could occur, fourth, and so on and so on, up to 30 days. So each one of these days has a probability of x sub I is equal to 1 over 366 days, where x sub I is equal to 1, 2, 3, all the way to 30. So all I'm saying is that each one of these days has a probability of 1 over 36. So remember that our event E was, what was our event E actually? I don't remember. Well, I do, but I want to write out the exact same one so we can stay consistent. So this is our event E, selecting a day in April. That's our event E. So now where we could look at P of E is pretty much the probability of 1 plus the probability of 2 plus the probability of 3 plus all the way to the probability of 30, where those numbers represents, obviously, the days. First day, second day, third day, fourth day, fifth day, sixth day, all the way to the 30th day. Well, this is 1 over 366 plus 1 over 366 plus 1 over 366 plus all the way to 1 over 366. In the end, we already know that our solution is 30 over 366, which is reduces to 5 over 61 if you really want to reduce this. I know I didn't reduce it, but you can reduce this if you want. So that's another way of looking at it. Now, why is this another way of looking at it? Because it kind of, this, how can I say this? By looking at it like this, it can make other problems much simpler to solve, specifically when they're not, when it's not considered fair. So what do I mean by that? Let's look at this example here then. Find the probability of an even number appearing when a loaded die is rolled such that 2 is 4 times more likely to appear as each of the other 5 numbers on the die. As each of the other 5 numbers on the die. So in other words, what I mean by a loaded die, a loaded die pretty much is a cheating die. A die in which it's loaded in the sense that it's going to come out with more specific, with the numbers that you specifically want. There's a higher chance of it coming out for specific numbers. In this case, there's a higher chance of the 2 coming out than any other of the other numbers. So how do we do this? Well, here we go. Find the probability that an even number appearing when a loaded die is rolled such that 2 is 4 times more likely to appear as each of the other 5 numbers on the die. Okay, so let's determine our events. First of all, what is it that we want? What is it that we're looking for? What is our event? What is our event? Rolling an even number, exactly. Rolling an even number And the possibilities are 2, comma, 4, comma, 6. So we're only in an even number. Since we only have one die, these are the only 3 possibilities, 2, 4, 6. That's it. Those are the only even numbers in a 6-sided die. Right? Obviously, this is in a fair 6-sided die. Obviously, this die is loaded, but we'll get to that in a sec. So, in a 6-sided die, to have an even number, the only possibilities are 2, 4, 6. Okay. Now, notice that this die is loaded. Where a loaded die is rolled such that 2 is 4 times more likely to appear as such as each of the other 5 numbers on the die. So that means that 2 has a 4 times higher chance of appearing than any other number. Okay. So that means that the probability of 1 appearing is exactly the same thing as the probability of 3 appearing, which has the same probability as 4 appearing, which has the same probability of 5 appearing, and which has the same probability as 6 appearing. And what is that probability? Well, what is that probability? Mm, 9/16, not quite. What is the probability of 1, 3, 4, 5, and 6 appearing? Not 9/16. 1/9, exactly. 1/9. So probability of each one is occurring is 1/9. Now, okay. Now, why 1/9? Well, there's the probability of 2 appearing 4 times is more likely than any other number. So that means, oh, you did 1/8. No, not 1/8. It's actually 1/9. Because 1, 2, oh, forgetting 2. 1, 3, 4, 5, 6. Those are 5 numbers. And then the 2 can appear as 4 times more likely. So 2, 2, 2, 2. So technically there's 9 outcomes. So 1/9. But keep in mind that the probability of 2 is 4 times more likely to appear as each of the other numbers. Okay. So that will be probability of whichever one, let's say 1. So that's 4 times 1/9. So that's 4/9. Does that part make sense so far? And we're not done with the problem. We haven't even answered the question yet. Or the statement, actually, because it's not more of a question, it's more of a statement. We haven't answered the statement yet. Any questions on any of this part first? You can write out the sample space if you want as well. It'll be 1, 2, 2, 2, 2, 4, no, not 4, 3, 4, 5, and 6.
Professor,
Mhm.
can you explain how you got 1/9 again?
So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. When I write out the sample space. So that means the probability of 1 showing up is 1 out of 9. Probability of 2, 3 showing up is 1 out of 9. Probability of 4, 1 out of 9, so on and so on.
Got it. Thank you.
Okay. Any other questions? So the probability of 2 showing up is 4 times either one of those numbers, which is 4/9. But we want the probability of an even number appearing. which an even number is 2, 4, 6. So that means that the probability of this event is actually the probability of 2 plus the probability of 4 plus the probability of 6, which are my even numbers. So that's 4/9 plus 1/9 plus 1/9. That just is simply 6/9, which is 2/3. Yes, 2/3. Any questions on that? No? Okay. And this actually leads us to, so the idea of adding these up to help us find this probability leads us to the next definition. And I'll leave this up there for a couple of seconds. So that way, just in case you didn't get it down. Okay, this leads us to this definition. The probability of the event E is the sum of the probabilities of the outcomes in E. That is, P of E is equal to the summation of S belonging in E, P of S. Now, this ain't capital S, so this doesn't mean like the sample space. Any questions on that? And this definition still coincides with pretty much what we did in section 7.1, where if you add them all up, it should equal to 1. And it will. Good. Any questions? Okay. Now this is the same thing as this definition, this theorem 7.2.1. The only difference is, obviously, it's just making the connection between union and summation. If E sub 1, E sub 2, and E all the way to, well, actually an infinite amount, is a sequence of pairwise disjoint events, meaning they don't have nothing in common, in a sample space S, then the probability of the union, as it starts at 1, of E sub I, which is the event, is equal to the summation of I, which starts at 1, and P, the probability of E sub I. Let's see, just call this I, because we already know that I starts at 1. I'll just leave it as it is, same thing. Good. Any questions so far? Okay. Now, we're not done with this section, but we only have like a couple more minutes, probably like 9 minutes left. And the next example is not going to take that long, but I kind of want to start off with the next lecture with this next example. So we're going to stop here. If you have any questions, let me know. Other than that, we're just going to stop here. Any questions? No? Okay. So again, we're going to be dealing with probabilities for chapter 7. That's what we're going to be dealing with. So expect a lot on probabilities. And that's pretty much it. Your exams, I'm going to grade them. Honestly, I haven't even started them yet. Haven't even downloaded them yet. So I'll look at them. But hopefully I'm trying to get them done this week. That's what I'm trying to, but we'll find out. But other than that, that's pretty much it. So I'll see you guys next time. If you have questions, let me know.